All right, so we've done fundamental theorem of calculus 2, and now we're ready for fundamental theorem of calculus 1. All right, so now I still have it on the blackboard to remind you. It says that the integral of the derivative is the function, at least the difference between the values of the function at two places. So the place where we start is that with this property that f prime is equal to f. That's the hypothesis. Now, unfortunately, I'm going to have to assume something extra in order to use the fundamental theorem of calculus 2, which is I'm going to assume that f is continuous. That's not really necessary, but that's just a very minor technical point, which I'm just going to ignore. All right, so we're going to start with f prime being equal to little f. And then I'm going to go somewhere else. I'm going to define a new function, g of x, which is the integral from a to x of f of t dt. Now, this is where we needed all of the labor of Riemann sums, because otherwise we don't have a way of making sense out of what this even means. All right, so hiding behind this one sentence is the fact that we actually have a number, we have a formula for such functions. So there is a function g of x, which once you've produced a little f for me, I can cook up a function capital G for you. Now, we're going to apply this fundamental theorem of calculus 2, the one that we've already checked. So what does it say? It says that g prime is equal to f. And so now we're in the following situation. We know that f prime of x is equal to g prime of x. All right, that's what we've got so far. And now we have one last step to get a good connection between f and g, which is that we can conclude that f of x is g of x plus a constant. Now, this little step may seem innocuous, but I remind you that this is the spot that requires the mean value theorem. So in order not to lie to you, we actually tell you what the underpinnings of all of calculus are. And they're this. The fact, if you like, that if two functions have the same derivative, they differ by a constant. Or that if a function has derivative 0, it's a constant itself. Now that is the fundamental step that's needed, the underlying step that's needed. And unfortunately, there aren't any proofs of it that are less complicated than using the mean value theorem. And so that's why we talk a little bit about the mean value theorem, because we don't want to lie to you about what's really going on. Yes?
From the fundamental theorem to f prime of x, which is g prime.
The question is, how did I get from here to here? And the answer is that if g prime is little f, and we also know that f prime is little f, then f prime is g prime. Okay? Other questions? All right, so we're almost done. I just have to work out the arithmetic here. So I start with f of b minus f of a. And that's equal to g of b plus c minus g of a plus c. And then I cancel the c's. So I have here g of b minus g of a. And now I just have to check what each of these is. So remember the definition of g here. G of b is just what we want, the integral from a to b of f of x dx. Well, I call it f of t dt. That's the same as f of x dx now because I have the limit being b and I'm allowed to use x as the dummy variable. Okay? Now the other one I claim is 0 because it's the integral from a to a. All right, this one is the integral from a to a, which gives us 0. So this is just this minus 0, and that's the end. That's it. This is, I started with f of b minus f of a, I got to the integral.